This session is purely mathematical. We're going to talk about a technique used to solve the Legendre equation. I'm guessing you can't see it, but here is the form of Legendre's equation. Now, in the previous session, we had something a little bit different. Instead of just a constant here, we had a term. I'll just read it out to you because you can't see it, but it was in brackets. We had lambda over h bar squared minus m squared over 1 minus z squared. Now here, there's no variable like z, or in this case x. It's just a constant. So this is Legendre's equation. So I suppose the equation we had before with the m squared over 1 minus z squared, I guess that's what's meant by the associated, like similar to, but not the same thing. So I guess my guess is that's where the adjective associated came from. So what we got, the equation that we got for the eigen equation was the associated Legendre equation, whereas this is the Legendre equation per se. So I suppose we'll get a solution to this, and then we will adapt it to our AngularMmntm type associated Legendre equation. That's my guess. All right. Okay. So this is the Legendre equation here, and lambda here is just a constant, right? And we're trying to solve for these p's, and p for polynomial. So we'll start talking, in a sense, talking about these Legendre polynomials, which are solutions to Legendre's equation, which is this, where lambda is a constant, right? Okay, so you have a look at that equation and you ask yourself, how might you solve it? Now, if you're an expert in differential equations, you'd probably just jump to it and say, oh, well, easy, just express P as a power series. In other words, a sum of weighted powers of X. So something of this form. So you assume that this P, the solution here to this equation, is of the form of a sum of weighted powers of X. Right? Now you may ask, well, what's this thing doing out here? It works. Okay, and these powers range from k. These are integer powers, so ranging from, and positive integer non-negative integer powers. So ranging from k is 0 to plus infinity. So you're assuming that, so when k is 0, it's just 1, so you have a0. So you're assuming that the a0, a suffix 0, so a0, is non-zero. Okay? That's built into this assumption. All right. So you assume this is what's usually called, and I've mentioned this a few times in the past, an Ansatz, a German word, A-N-S-A-T-Z, Ansatz. And an Ansatz is a trial solution, right? It's a solution that you think might work, but you're not 100% certain. So it's a trial. You're testing it to see if it works. So a suggested solution, if you like, an Ansatz. This is an Ansatz. All right, plug it in. So put this value for p, plug it into here. You differentiate, and you will get something. It's a bit more complicated. Something of this form. So if you differentiate p with respect to x, you'll get a k coming outside, and then you'll x to the k minus 1 term here. You're differentiating it again, so you'll get k to the minus 2. So you get this kind of stuff These coefficients come from the differentiation, so yeah, I'll ask you to do that also as homework. Any sort of fairly routine derivation, from line to line, I ask you to do. So plug this into here and here. Do all the differentiation, and you'll get this. Okay, so I ask you to do this. Now, what have you got here? You've got a sum of weighted terms. These terms here are of powers of x. Now, what's the smallest power of x you can get in this equation? Well, now remember k ranges from 0 to infinity, so the smallest power of x in this term here, well, in the whole sum, would be x to alpha minus 2, right? Because k is 0. Now, if k is not here, you've got x to the alpha, but this is x to the alpha minus 2. So this one here, that's the smallest power of x, right? Here, x. And what's its so when k is nothing, what is this power of x? What is its coefficient? In other words, what's this? Well, this. So you have a naught, right? Because k is 0. So you have a naught. Here it is here, a naught. Times alpha into alpha minus 1. Alpha into alpha minus 1. So that is your coefficient for the smallest power of x, which is alpha minus 2, which is when k is 0. Okay? Alright? So, now for the left-hand side here to be 0 for all powers of x, it means that the coefficients here, the coefficients of each power of x must be 0. Follow that logic? So I'll say it again a different way. You can rewrite this here in powers of x. You find the coefficient of the power of x. And the left-hand side is equal to 0. So that means the coefficient of each power of x must be 0. Right? And that includes for the smallest power. The smallest power of x is alpha minus 2. So its coefficient, which is this one, a naught alpha times alpha minus 1, must be 0. Because every coefficient of a power of x must be 0. So this is 0. And that implies that alpha, from here, if this is 0, then either alpha is 0 or alpha is 1. Okay, from here. So we know that alpha is 0 or 1. Alright, now have a look at this, and what is the coefficient for a general power of x? Just some arbitrary power of x. So you'll get let's see. So you'll get a contribution from here and a contribution from here. So it'll be like 2 contributions. So again, I ask you to do this for homework. So in general, the general coefficient, or the coefficient of the general power of x, will be of this form. Okay, so when x is what's the power of x for which this would be true? Is it k? Or k plus 2? Well, whatever. Derive this coefficient. That's your coefficient of a general power of x. Okay? And that whole thing has to be 0, because every coefficient of any power of x has to be 0. So this, which is the general form of a coefficient of a power of x, that has to be 0. Now that's interesting, because if this is 0, then we then get a relationship between this and this. So take this, now that whole thing is 0, so take this, put it over on the right hand side. So